Now that we have learned about the structure of atoms, atomic number, mass number, neutrons, neutral atoms, and ions, the next important concept is the atomic mass unit, commonly abbreviated as AMU or simply U. The atomic mass unit is a special unit of mass designed specifically for measuring the masses of atoms and subatomic particles. Scientists use this unit because atoms are incredibly small, and measuring their masses in ordinary units like grams or kilograms would produce unimaginably tiny numbers that are difficult to work with. Therefore, instead of using grams, scientists developed a much more convenient unit called the atomic mass unit. To appreciate why this unit is needed, think about the size of an atom. An atom is so tiny that millions of atoms can fit across the width of a human hair. The mass of a single atom is even smaller. For example, the mass of one hydrogen atom is approximately 0.00167 grams, or 1.6710 grams. Writing and calculating with such extremely small numbers would be inconvenient and increase the chances of calculation errors. Therefore, chemists and physicists introduced the atomic mass unit to make atomic masses easier to understand and compare. The modern definition of the atomic mass unit is based on the carbon-12 atom. Scientists defined one atomic mass unit as exactly 1/12 of the mass of a carbon-12 atom. Carbon-12 was chosen because it is a stable and abundant isotope of carbon that serves as an excellent international standard. This definition allows scientists all over the world to measure atomic masses consistently and accurately. Although this definition may sound technical, there is a much simpler way to understand it. The mass of one proton is approximately 1 AMU, and the mass of one neutron is also approximately 1 AMU. Electrons are much lighter. In fact, the mass of one electron is only about 1 flak 1836 the mass of a proton. Because electrons contribute such a tiny amount to the total mass of an atom, their mass is usually ignored when estimating atomic masses. This means that if an atom contains 6 protons and 6 neutrons, its approximate atomic mass is 12 AMU because 6 protons contribute about 6 AMU and 6 neutrons contribute another 6 AMU. Similarly, oxygen contains 8 protons and 8 neutrons, giving it an approximate atomic mass of 16 AMU. Sodium has 11 protons and 12 neutrons, giving it an approximate atomic mass of 23 AMU. These simple calculations show why the atomic mass of many elements is very close to their mass number. The illustration emphasizes that one proton has a mass of approximately 1 atomic mass unit, and one neutron also has a mass of approximately 1 atomic mass unit. This approximation is accurate enough for most introductory chemistry calculations. Since electrons contribute very little mass, they are usually neglected when calculating the approximate mass of an atom. You may now notice an interesting connection between mass number and atomic mass. The mass number is the total number of protons and neutrons in the nucleus, while the approximate atomic mass in AMU is also determined mainly by the protons and neutrons because each contributes about 1 AMU. This is why the numerical value of the mass number is usually very close to the atomic mass expressed in atomic mass units. For example, carbon-12 has a mass number of 12 and an atomic mass of approximately 12 AMU. Oxygen-16 has a mass number of 16 and an atomic mass of approximately 16 AMU. However, students should remember that mass number and atomic mass are not exactly the same thing. The mass number is simply the count of protons and neutrons, so it is always a whole number. Atomic mass, on the other hand, is the actual measured mass of an atom expressed in atomic mass units. It may not always be a whole number because protons and neutrons are not exactly equal to 1 AMU, and electrons contribute a very small amount of mass. In addition, the atomic masses listed on the periodic table are weighted averages of all naturally occurring isotopes of an element. For example, chlorine exists naturally as 2 major isotopes, chlorine-35 and chlorine-37. Because both isotopes occur naturally in different proportions, the average atomic mass shown in the periodic table is approximately 3545 AMU, not exactly 35 or 37. This decimal value represents the weighted average mass of all naturally occurring chlorine atoms. The atomic mass unit is used throughout chemistry because it makes comparisons between atoms much easier. Instead of saying that one atom has a mass of 1.9910 grams, scientists simply say that it has a mass of 12 AMU. This simpler unit makes calculations, chemical equations, laboratory work, and scientific communication much more convenient. Atomic mass units are also essential for comparing the masses of different atoms. Hydrogen has an atomic mass of about 1 AMU, helium about 4 AMU, carbon about 12 AMU, oxygen about 16 AMU, sodium about 23 AMU, and gold about 197 AMU. From these values, we can immediately tell that a gold atom is much heavier than a carbon atom, while a carbon atom is much heavier than a hydrogen atom. The concept of atomic mass unit is also important in many branches of science. In chemistry, it is used to calculate molecular masses, molar masses, and chemical formulas. In physics, it helps scientists study atomic nuclei and nuclear reactions. In biology, it is used to determine the masses of proteins, DNA molecules, and other biological compounds. In medicine, isotopes with known atomic masses are used in diagnostic imaging and cancer treatment. In astronomy, scientists use atomic masses to understand the composition of stars and planets. Another important fact is that the atomic mass unit provides a bridge between the microscopic world of atoms and the macroscopic world we observe every day. Although individual atoms are far too small to weigh on an ordinary balance, using atomic mass units allows scientists to compare them accurately and predict how enormous numbers of atoms behave during chemical reactions. A useful way to visualize this is to imagine measuring the weight of a single grain of sand. Using a large industrial weighing machine would not be practical because the grain is far too light. Instead, you would need a much more sensitive instrument designed for tiny masses. In the same way, grams and kilograms are suitable for everyday objects, but atoms are so incredibly small that scientists needed a specialized unit, the atomic mass unit, to measure them accurately. So, whenever you study atomic masses, remember these important points. Atoms are too small to measure conveniently in grams, so scientists use the atomic mass unit. 1 AMU is defined as 1/12 of the mass of a carbon-12 atom. 1 proton has a mass of approximately 1 AMU. 1 neutron has a mass of approximately 1 AMU. The mass of 1 electron is extremely small and is usually ignored in basic atomic mass calculations. Understanding the atomic mass unit is essential because it prepares you for advanced topics such as relative atomic mass, molecular mass, molar mass, Avogadro's number, the mole concept, stoichiometry, and chemical calculations. It is one of the fundamental measurement units in chemistry and provides the foundation for understanding how scientists compare the masses of atoms, molecules, and chemical substances with remarkable accuracy. Now that we understand the basic structure of the atom and the role of electrons, the next important concept is electron shells, also known as energy levels. Electrons do not move randomly around the nucleus. Instead, they are arranged in specific regions surrounding the nucleus called electron shells, or energy levels. These shells represent the different distances from the nucleus where electrons are most likely to be found. Each shell has a fixed energy, and electrons occupy these shells according to well-defined scientific rules. This arrangement of electrons is called the electronic configuration of an atom and is one of the most important concepts in chemistry because it determines an element's chemical properties and how it reacts with other elements. To understand electron shells, imagine the nucleus at the center of the atom like the sun at the center of the solar system. Just as planets revolve around the sun at different distances, electrons occupy different energy levels around the nucleus. However, unlike planets, electrons do not travel in perfectly fixed circular paths. According to modern quantum mechanics, electrons exist in regions called orbitals, where there is a high probability of finding them. For beginners, however, the shell model provides an excellent way to understand how electrons are organized around the nucleus. The shells surrounding the nucleus are named K, L, M, NO, P, and Q. These names correspond to the principal energy levels numbered 1, 2, 3, 4, 5, 6, and 7, respectively. The K shell is the first shell and is the closest to the nucleus. The L shell is the second shell, followed by the M, N, O, P, and Q shells. As we move farther away from the nucleus, each shell becomes larger and has a higher energy than the previous one. The shell nearest to the nucleus has the lowest energy, while shells farther away have higher energy. This means that electrons in the K shell possess less energy than electrons in the L shell, and electrons in the L shell have less energy than those in the M shell. As the shell number increases, both the distance from the nucleus and the energy of the electrons increase. This is why the illustration shows the sequence: nucleus K, L, M, N, O, P, Q. Each shell can hold only a limited number of electrons. It cannot accommodate an unlimited number because each energy level has a specific capacity determined by quantum mechanics. The maximum number of electrons that a shell can hold is calculated using the formula maximum electrons tech-techant, where n is the principal quantum number or shell number. For the K shell, n-1. Maximum electrons tech2 duck2 electrons for the L shell, n-2. Maximum electrons, tech2, W8 electrons for the M shell, NW3. Maximum electrons, tech2, 18 electrons for the N shell, NW4. Maximum electrons, tech2, tech32 electrons. Similarly, the O, P, and Q shells can hold even larger numbers of electrons according to the same formula. However, in introductory chemistry, students usually focus on the first 4 shells because they are sufficient for understanding most common elements. Although these shells have maximum capacities, electrons do not simply fill them to their maximum before entering the next shell. Instead, electrons always occupy the lowest available energy level first. This is known as the Aufbau principle, which states that electrons fill lower energy orbitals before higher energy orbitals. Nature always prefers the most stable arrangement, and lower energy shells are more stable than higher energy ones. For example, hydrogen has only 1 electron, so that electron occupies the K shell because it is the lowest energy shell. Helium has 2 electrons, and both occupy the K shell, completely filling it. Since the K shell cannot hold more than 2 electrons, the next electron in lithium must enter the L shell. Therefore, lithium has an electron arrangement of 2-1, meaning 2 electrons in the K shell and 1 electron in the L shell. Let us look at a few more examples. Carbon has 6 electrons. The first 2 fill the K shell, while the remaining 4 occupy the L shell. Therefore, its electron configuration is 2-4. Oxygen has 8 electrons, giving it the arrangement 2-6. Sodium has 11 electrons. The first 2 occupy the K shell, the next 8 fill the L shell, and the remaining 1 enters the M shell. Therefore, sodium has the electron configuration 2008-1. This arrangement of electrons is extremely important because the outermost shell, also called the valence shell, determines the chemical behavior of an element. The electrons present in the outermost shell are known as valence electrons. These electrons participate in chemical reactions and chemical bonding. Atoms gain, lose, or share valence electrons to achieve greater stability. For example, sodium has only 1 electron in its outermost shell. It is much easier for sodium to lose this 1 electron than to gain 7 more. Therefore, sodium loses one electron and forms a Na ion. Chlorine, on the other hand, has 7 electrons in its outermost shell. It is easier for chlorine to gain 1 electron than to lose 7. Therefore, chlorine gains 1 electron and forms a Cl ion. These two oppositely charged ions attract each other and form sodium chloride, or common table salt. The arrangement of electrons in shells also explains why elements in the same group of the periodic table have similar chemical properties. For example, lithium, sodium, and potassium each have 1 valence electron, so they all react in similar ways. Fluorine, chlorine, and bromine each have 7 valence electrons, giving them similar chemical behavior as well. Thus, electron configuration provides the foundation for understanding the periodic table. It is also important to remember that the shells shown in simple diagrams are not the actual paths followed by electrons. According to modern quantum mechanics, electrons exist in orbitals, which are regions where there is a high probability of finding an electron. The shell model is a simplified representation that helps students understand the arrangement of electrons before studying more advanced quantum theory. The farther an electron is from the nucleus, the weaker the attractive force between the negatively charged electron and the positively charged nucleus. Therefore, electrons in the outermost shell are held less tightly than those closer to the nucleus. This is why valence electrons can be removed or shared more easily during chemical reactions. Electron shells are also closely related to energy changes. When an electron absorbs energy, it can move from a lower energy shell to a higher energy shell. This process is called excitation. However, the excited state is unstable. Eventually, the electron returns to its lower energy shell, releasing the absorbed energy as light or other forms of electromagnetic radiation. This phenomenon explains the colored flames seen in flame tests and the emission spectra used to identify different elements. Understanding electron shells is essential because they explain many important chemical concepts, including electron configuration, valence electrons, chemical bonding, ion formation, periodic trends, atomic size, ionization energy, and chemical reactivity. Nearly every topic in chemistry builds upon the arrangement of electrons within these energy levels. A simple way to remember this concept is to think of the nucleus as the center of a building and the electron shells as different floors. The first floor, or K shell, is closest to the center and can accommodate only 2 electrons. Once it is full, new electrons move to the second floor, the L shell, which can hold 8 electrons. As more electrons are added, they continue filling higher floors according to the available space and energy. Just as people usually fill the lower floors before moving to higher ones, electrons always fill the lowest energy shells first. So, always remember these important facts. Electrons are arranged around the nucleus in shells called energy levels. The shells are named K, L, M, N, O, P, and Q. The K shell can hold a maximum of 2 electrons. The L shell can hold a maximum of 8 electrons. The M shell can hold a maximum of 18 electrons. The N shell can hold a maximum of 32 electrons. As the shell number increases, the distance from the nucleus and the energy of the electrons also increase. Electrons always fill the lowest energy shells first, and the electrons in the outermost shell determine the chemical properties of an element. Understanding electron shells is one of the most important milestones in learning atomic structure because it connects the structure of atoms with chemical bonding, periodic trends, the formation of ions, and virtually every chemical reaction that occurs in nature.